Solar sails, a groundbreaking propulsion technology in the field of space exploration, offer revolutionary potential for space travel. Originated in the 17th century, the idea, much like the sails used in maritime ships, takes its motivation from the natural world, using the pressure from photons and sunlight for propulsion. The theory, long confined to the realm of speculation, finally took shape in the 21st century as a cornerstone of propellantless propulsion strategies for the journey into deep space. Johannes Kepler, a 17th century astronomer, was the first to conceive of solar sails. Observing comet tails being blown by what he believed to be a solar breeze, Kepler conjectured that vessels might one day sail through space, driven by the pressure from sunlight. However, it wasn't until the advent of the space age and the development of ultra-lightweight and durable materials necessary for solar sails that his vision began to be realized. The lunar missions of the 20th century marked the beginning of the history of solar sails. The significance of solar sails lies in their potential to reimagine space travel. The ability to harness the sun's energy, thereby saving on propellant weight, could create transformative opportunities for space missions. Solar sails can continue to accelerate over time, eventually reaching high speeds, making them an ideal form of propulsion for interstellar missions. They also could be deployed for operation of Earth-observing satellites, asteroid deflection, and even powering spacecraft to distant planets in reasonable timeframes. Solar sails exert continuous positive acceleration, albeit small, which increases over time regardless of the distance from the sun, until it reaches an incredible speed. This counters the traditional propellant-based propulsion that requires enormous amounts of fuel to cover vast distances, bringing both economic and environmental advantages. With unlimited sunlight as fuel, solar sails offer a relatively inexpensive and renewable resource for space exploration. Moreover, solar sails are autonomous, requiring minimal human interaction once launched. This significantly minimizes the risks associated with human errors, enhancing the safety and reliability of the missions. On the flip side, several equally compelling challenges are associated with solar sail technology. One of the primary limitations of solar sails is their dependency on sunlight. The efficiency of a solar sail decreases as the vessel moves farther away from the sun due to the reduction in solar intensity, thereby limiting the technology's application to inner solar system missions. Solar sails require extremely large surface areas to capture sufficient sunlight and generate enough propulsion. Designing, manufacturing, deploying, and controlling such large structures in the harsh environment of space are significant challenges. Additionally, the lightness of the materials means that solar sails can be vulnerable to micrometeoroid damage. Since they depend on momentum transfer from impacting photons, solar sails by nature come with limited thrust, and therefore, acceleration is slow. Moving a spacecraft to a specific location at a particular time may not be feasible. Also, while the long-term operation of a solar sail can be autonomous, the initial deployment sequence remains a critical phase. Any deployment failure could cripple the mission, and given the immense distances such missions operate at, there would be no practical means for human intervention to correct any issues. In densely populated space segments with other active missions, this could raise safety concerns due to the high speed and uncontrollability of failed missions. Despite the challenges as advances in materials science and space engineering continue, it's not inconceivable that entire fleets of solar sailing vessels could one day be gliding through our solar system, propelled by the rays of the sun, fulfilling Kepler's centuries-old vision.